So good afternoon. I will be talking about our fixation and stimulus channel for AO imaging. I work closely with my colleague Marcel on this project as he started by developing the stimulus channel. Starting from background, I will describe the overarching objectives of the channel, followed by design and implementation. Then I will show validation and applications in adaptive optics OCT imaging. AO ophthalmoscopes measure and correct ocular wavefront aberrations, enabling cellular resolution retinal imaging and stimulation. Like microscopes, the inherently small field of view and high magnification of AO ophthalmoscopes make them highly sensitive to the subject's direction of gaze and ability to fixate. Most AO ophthalmoscopes therefore have an additional optics channel with a visible, controllable target that is wielded by the subject to control which patch of retina is imaged. Perhaps because of its simplistic role, the fixation channel is probably the least reported component of AO ophthalmoscopes, with few details given in the literature and only one publication that we know of devoted to this topic. Yet, this channel is challenging to develop because its design must conform to the requirements of AO imaging and visible stimulus channels. It is in this context that we develop a more powerful integrated fixation and stimulus channel. The previous work I mentioned employed custom optics and mounts, so the cost and lead time can be high. The field of view is also insufficient for many applications. Here we use stock lenses and achieve a larger field of view. We have several overarching objectives of the fixation and stimulus channel. We want the steering field of view of the fixation target to extend beyond the nasal rim of the optic disc, covering the fundus area most critical for monitoring disease. We want the working distance between subject and our system to be several centimeters to accommodate different head shapes and thick facial hair. We want to correct 20 diopters range of spherical refractive errors to cover the vast majority of population. Otherwise, a fuzzy fixation target is not precise for fixation and reduces repeatability in longitudinal studies. To study retinal function properly, we need accurate control of stimulus intensity, duration, and wavelengths. The last requires high background light suppression. We also need sufficient irradiance illuminance on the retina, which requires low light loss. Next, I will describe our design and implementation of the channel. This is the fixation channel optics. We use a telescope formed by lens 2 and 3 to correct the eye's spherical refractive error. Some people call this a Badal system, with lens 3 being the Badal lens. By adjusting the distance between lens 2 and 3, we can generate different versions on the eye to accommodate different refractive errors. The eye's nodal point overlaps with the second focal point of the lens 3, so that the angular location of the fixation target does not change with axial eye length. We use lens 1 to image the fixation target to infinity, which provides the object for the telescope. It is also beneficial to place the fixation target at the far point of the eye because it minimizes accommodation fluctuation, which causes dynamic aberrations. To change the distance between lens 2 and 3, we put the component before lens 3 on the translation stage. Here, we determine the translation stage travel range to correct for 20 diopters range of refractive error and show how it trades off with working distance. In the myopia case, the focal length of lens 2 is shifted to lens 3 by x, generating a diverging beam on the eye. The divergence of the beam is related to the distance of the virtual object, which is minus x prime away from the second focal point. By using the Newtonian form of the lens equation, we can calculate the shift of the focal point x, which is proportional to the divergence on the eye. To correct for a range of refractive errors delta p, we need to translate the stage by delta x. We see that the required stage travel range is proportional to f3 squared, while f3 is proportional to the working distance. Therefore, a large working distance requires a long stage travel range, which increases cost and system size. To correct for 20 diopters range of refractive error, we need a stage travel range of 4 inches for Badal lens of 14 diopters. There's also a trade-off between working distance and field of view. An off-axis point on the fixation display is mapped to an angle at the eye. Hence, the maximum angle that lens 3 subtends to the eye determines the field of view of the fixation target, of the fixation channel. To maximize field of view, we need to maximize this angle by using a large lens and placing the lens close to the eye. However, a diachroic mirror needs to be placed between lens 3 and the eye to combine with AO imaging beam. This limits how close lens 3 can be placed to the eye and hence the angle of lens 3. Therefore, there's a trade-off between subject working distance and fixation channel field of view. For implementation, we use a camera lens for lens 1, which has 7 elements. For lens 2, we use 2 inverted doublets to create a focal length of 250 millimeters. For lens 3, we use a thin, spherical lens with a focal length of 71 millimeters to achieve good image quality and large working distance. The lens appeared to be in the wrong orientation, but we found this orientation gives better image quality as confirmed by ZMAX simulation. We use a doublet for the simulation because the company does not disclose the lens data. The flipped orientation reduces distortion. We use an LED display to present a white cross as the fixation target. Different from reference 2, we use a third-party driver board that is more compact and holds the display in its geometric center. This allows us to mount the driver board and the display on a rotation mount in a cage system. The high brightness of the display enables us to combine fixation and stimulus channels with a 10% transmission, 90% reflection beam splitter. This increases the stimulus beam throughput by almost twice compared with using a 50-50 beam splitter. Now let me describe our stimulus channel, which is used to study retinal function. We use a supercontinuum laser as the source, whose spectrum is shown here. The laser is spectrally and temporally controlled by an acousto-optical tunable filter, which outputs any wavelengths between 430 to 670, with a full width half maximum bandwidth less than 1.8 nanometers. However, there is some background light that can stimulate photoreceptors. Hence, we use spectral filters to reduce the background light by 60 dB. We use a mechanical shutter to block the small amount of leakage light during subject alignment. Then, the light is coupled to a multimode fiber. Finally, we image the fiber core onto the retina with 3 optical relays, with the eye being the last lens. Considering our imaging field of view and eye motion, we designed the stimulus patch size on the retina to be 2 degrees. This determines the fiber core's diameter to be 365 microns based on magnification. The next question is how to determine the numerical aperture of the fiber. We use Lagrange invariant. Lagrange invariant is a product of y and u, where y is the object height, n is the refractive index, and u is the ray angle. This product is conserved through the optical system. In our case, the fiber core is imaged onto the retina, and we can treat the optics in between as a black box. The maximum Lagrange invariance supported by the eye is calculated to be 0.06 when the eye is dilated. The Lagrange invariant of the fiber is related to its NA. The Lagrange invariant of the fiber should be smaller than the maximum Lagrange invariant of the eye. Otherwise, there's energy loss inside the system. From this, we found that fiber NA should be smaller than 0.33. What happens if we use an NA larger than 0.33? In this case, the beam size is bigger than the eye pupil size, and some light will be blocked by the iris. This causes light loss, which is not good. On the other hand, the fiber NA should not be too small either. When fiber NA is small, the beam size on the eye is very small. If the eye is displaced laterally from the beam, the coupling efficiency to photoreceptors decreases. In this case, the stimulus efficiency is sensitive to eye alignment, which should be avoided. Once we have the fixation stimulus channel, we need to combine them with the AO imaging beam. We use a diachroic mirror with low light loss, low wavefront error, and low group delay dispersion for OCT. The diachroic mirror was cut along a parabolic curve and mounted on a 3D printed aluminum conic holder to increase the working distance by minimizing potential contact with subject's face. The working distance is not only related to the eye, but also related to subject's chin and beard. The subject's beard should not touch the mirror that reflects the AO imaging beam or block any imaging beam. To increase the working distance, we position the diaphragm mirror at 42 degrees instead of the conventional 45 degrees, resulting in a slight tilt of the AO imaging beam by 6 degrees. The improved working distance is calculated to be 13 millimeters. Next, I will talk about validation and application of the system. Here's a photo of a subject in our system. There's sufficient distance between his beard and the mirror. His eye is about 30 millimeters away from the top of the diaphragm mirror. This working distance is sufficient for all subjects imaged to date. Then we validate the large field of view of the fixation channel. We first calibrate the relationship between visual angle and fixation target size on two subjects with different axial islands. The calibration result was 16 pixels per degree for both subjects, independent of axial islands, as expected from the Badal principle. Then we moved the fixation target to the edge of the subject's field of view and recorded the location beyond which they could no longer see the target. We found the field of view of the fixation channel to be 40 degrees horizontally and 37.5 degrees vertically, extending well beyond the optic disc and vascular arcades, as can be seen from this clinical image taken by a wide field imaging lens. Our fixation channel achieves a large field of view which allows us to image anywhere within the red circle. Next, I will show some AOCT imaging results at 20 degrees. This is the inner segment, outer segment junction image. We can see the multimode structure. This is the cone outer segment tip image. This is the RPE cell image. If I toggle between the RPE and cone cell image, you can see the cones fill in the holes of the RPE cells, and they align quite well. Therefore, the cone to RPE cell ratio is 1 at 20 degrees, which has not been measured before at this eccentricity. This result is very different from the case closer to the fovea, where we see multiple cones sharing one RPE cell. These are the macrophage cells near the inner limiting membrane. These are the ganglion cell somas. We also observed one presumed displaced ganglion cell in the inner nuclear layer. Then we performed functional imaging of the retina at 20 degrees by doing optoretinography. Compared with previous work, we also developed a time-saving protocol where we double stimulate the retina with 2 flashes of light in one video. Cones were then classified from the phase responses. The cone outer segment length at 20 degrees is only 9 microns instead of 30 microns at lower eccentricities. This makes data processing much more challenging. Here we show the classified cones overlaid on the mosaic. In summary, using all stock components except one 3D printed mount and some machine adapter plates, we balanced the trade-off between working distance, steering field of view, dioptric correction range, and stimulus light efficiency, and achieved better performance in all areas compared to our previous channel. This work extends the retinal regions and subject population that can be studied by AO ophthalmoscopy. As an example, we performed structural and functional imaging at 20 degrees. While intended for our AOCT, the design, components, and performance trade-offs are general enough to be applicable to many other AO ophthalmoscopes in the field. I want to thank my lab mates and the funding from NIH. Thank you for your attention.